we will be working with how do you manipulate these registers. How do you do that actually? So that's the main question that has been asked now. So I have a number of bit positions. So let's look at position TXC0. Well, that's position 6 because TXC0 is again equal to the constant 6, right? What does that mean? Well, what kind of bit value is stored at this particular position in this particular register? Well, it's transmit character complete. It's set when both entries in transmit shift register are empty or shifted out. It's not very useful because I'm more interested in this particular guy. It says if the bit at this position is being set, it says that transmit data is empty, and that goes high when one of the two buffers over here is empty, which means that I can already put in a character. I do not have to wait till both registers are empty, like the shift register and the transmit buffer. I'm okay if one of the two is empty, because then I can already push in a new character. So that's what I'm interested in. So when that happens, then it's time to refill. So that's why this has a default value of 1, right? Because when you start off with your code running on your MCU, there's nothing in the transmit buffer. So it is set at 1 because indeed both buffers are empty. So you can refill it. So then there's some other positions. For example, this one, suppose your baud rates were not synchronized properly between the laptop and your MCU, then those 4 samples that you have per bit will likely not start matching. And you will detect an error, and that error is coded up in this particular position. So FE0 again is a keyword, right? It's equal to the constant 4. I can read it out, this register, by taking the end of this register with the 8-bit value 1 left shifted over FEN. Then I will get this position, and if that's equal to a 1, then that means that I had a bad clock rate. So you can use that to do some debugging if that is needed. Alright. There's another error that can happen, a data overrun. So say you receive a character in your receive buffer, but you do not read it out fast enough, and another character is already being transmitted over from the laptop to you, to the MCU, and is overriding the data that was stored in the buffer but was not yet read out. Then you will see that this particular flag, right, so this particular position in this register is set to 1. So that's all very helpful if you want to do some debugging. Now there's much more. There is the parity error is being coded up in this particular position. You can set, these are positions that you can write. You're allowed to write, you have write permission. And how do you write, for example, this particular bit? I want to make sure it goes at double speed. Alright, twice the baud rate. Then I want to set a 1 in here. How do we do that? I take this register, it's a variable, and I'm going to put a 1 in here. Well, I do not want to change any of the other bits, right? So what do we do? I'm going to OR the 1 left shift over U2xn positions. So 1 left shift U2x0 is 1 left shift 1, I've replaced this by its constant value 1, which is going to be the factor 0, 1, 0, 0, 0, 0, 0, 0. Then I OR this register with that particular thing, and I get 0, and I only change this because I have a 1 here, when I left shift 1 over this amount of positions, so I get 0, 1, and everything else is left the same, including this particular one. So that's how I could do that. Now, and then there's some other stuff over here for multiple processors, but we don't care about that. So then we have a register B. Again, a whole bunch of special positions in this particular control register that are of interest to us. First, this particular position indicates the receive character complete interrupt enable. Again, later we'll go into detail about what interrupt service routines are. But if I want to make sure that the hardware will trigger an interrupt service routine that relates to this particular position, when that is set to 1, when that value over here is set to 1, then if you set this particular thing to, if you set this particular position to 1 in this register, right, the value at this position to 1, then the hardware expects an interrupt service routine for this. That means that if the received character is indeed complete, so let's go to the previous slide, which was this register, so this flag is being set to 1, right, the value over here, that will trigger a hardware event, that will trigger the ISR, and then you can do more stuff. Okay, lots more detail later on about all of this. We can also enable the interrupt for both of the members in the TX queue being empty. We can enable interrupt for the first of the output pipeline empty. We can, and this is also important, we can make sure that if you enable the RX and the TX, then that will disable whatever you have done before, will disable any other I/O settings for the pins D0 and D1. So they are now exclusively meant for the RX and TX, or receiver line and transmit line functionality. So for good householding, you will always set these to the proper values. So how do you do that again? You take this register and you OR it with the 1 left shift over this many positions, and also you OR it with 1 left shift over this many positions. So we'll see that I think in one of the next slides. Now, you see a UCSZ02 over here. Well, there's also a UCSZ01 and 00, and those 3 bits together, that is the bits associated to those positions, those 3 together you can look up in a table, and that will then indicate a certain setting, and that's on the next slide. So we have a control register C. Here you see the other UCSZ00 and 01, and you see also a UMSEL, and these 2 bits you can set in certain ways according to this table that you can find in the datasheet. And we will often use, we will always use asynchronous USART, but you can have other settings if you would have liked to do so. So here is the 3 bits that I was just talking about, and this actually sets your frame structure. So I can decide to have very short frames that only have 5 data bits, or very long ones that have 9 bits. In our case, you want to transmit characters between the console of your laptop and the MCU, so we transmit characters, and that will be 8 bits. Now the default setting is, by the way, that where is it? That this particular position in that control register C is set to 0, so we have 1 stop bit. We have no parity bits enabled. By default, those are also always 0. And so, in other words, the default frame setting, if you use an 8-bit character size, will be 10 bits. The 8 data bits plus a start bit plus a stop bit. Okay, so, and this table, you can look at it too, is related to how do you synchronize the 2 clocks at the receiving and transmit end. Now, finally some code. Alright, so the first thing that we need to do is we need to make sure that we know what the clock frequency is of our processor. So here it is. We want to know what kind of baud rate we need to use. This is the one that we're going to use. And now we have this define instruction that takes that formula that we had on one of the previous slides. So we go all the way back. I want to show you that once more, which is this particular formula. So FCPU divided by 16 divided by baud and then minus 1. So let's go forward again. Is exactly what's happening over here. You do an integer division with 16, then an integer division by baud. That result, you subtract 1 from it, from this. So that's a calculation that leads to a certain integer in the range from 0 to 4095 and can be represented by 12 bits. In my main program, I would like to call a special function, a procedure, which is sort of nice coding. You could put all of this also in your actual main code, but if you do it like this, then you can reuse this function across all your assignments where you need to initialize your UART. So I'm going to create a special procedure that takes as input this particular value. So it takes as input UBRR, that is what we see here. We see here unsigned integer. So the integer is represented as a positive integer without a sign. So otherwise we would have interpreted it as potentially a negative value. That's possible as well. Now, so we have this integer that comes in. What do we do? I'd like to explain these few code lines to you because they may look a little bit new. So first of all, I have an integer, and what am I going to do? I want to shift it. So I'm going to do some, if I do this, I'm shifting 8 bits out of my bit representation of that integer, and it means that the 4 most significant bits remain, and those 4 bits need to go into this register UBRR0H, which stores those 4 bits that are the highest, the most significant bits of my representation of this particular formula. Now, if I just do an equal sign over here, this is only an 8-bit register, right? And if you take an integer like this, you represent it as a bit string, which is 12 bits, it turns out you just copy over, the first 8 bits into that one. So now we have the lowest significant bits, the 8 lowest significant bits are pushed into this register, and then the next 4 more significant bits are being put into this UBRR0H register. So that will set the baud rate. Also notice that we do some typecasting, so this is all done as an unsigned character. So that's what we do. So these are simple one-line instructions that are short and concise, but it requires a little bit of interpretation, especially if you are not familiar with C or the syntax of C. Then I hope that my explanation was clear enough for you to be able to do this yourself later on at some point. Now, what do we want to do too? We want to make sure that the D0 and the D1 pins are only being used for your UART, and that means that in this control register, there are many ways to do this. We're going to just set those 2 bits related to those 2 positions to 1. So what was that again? So let's go back. That was register B, right? Now what is RXB? No, where was it? Sorry, these 2 ones, right? What is RXEN0 equal to? It's equal to 4. TXEN0 is equal to 3. Everything else is equal. So what do we do now? So look at this program. I'm going to left shift over those positions. That means I get here an 8-bit string, right? An 8-bit value, a byte value, that has exactly a 1 in this particular position and 0 elsewhere. This one has a 1 in exactly this position and elsewhere 0. So if I compute this, because I have an OR sign here, what do I get? I get a 8-bit string, an 8-bit byte, right? A byte that has a 1 in exactly this position and a 1 in exactly that position. And that is what I assign to this particular register. And I want all the other bits to be equal to 0. So that's how I initialize my UART. So what is the result then of this particular value? So let's go back. It will be equal to only those two positions, which are here and here. It will be equal to the value 0, 0, 0, 1, 1, 0, 0, 0. Okay, so the value, the initial value has been changed to 0, 0, 0, 1, 1, 0, 0, 0 after that one instruction. Okay, so that's the initialization, that's it. Now I have a difficult piece of code. So what I want to do is, I want to create what is called a file. That's a concept that you have not heard of either. A stream. So you can think of that as a stream of characters. And that stream is, you need to have functionality to manipulate that stream. You need to be able to add characters to the stream, and you need to be able to read characters from the stream. So how will this be connected? Well, what we're going to do is, in C, later on, we will connect this particular stream to the actual, UART communication that we're talking about here. So this is what's happening. So if I want to put a character, and this is a funny example, for example, I put the character C, which happens to be equal to this very strange character. This is not A, right? This is backslash A, it's a special symbol. And actually, if you look it up in the table of ASCII2 characters, there's one slide on that later on, then it represents an alarm. So maybe what I want to put actually on my console is something that says ring. And then I can get out. So it's just a funny example of how you can manipulate this type of code. More importantly is, for example, this particular guy. If I see a new line character, because I hit the return button, that will be interpreted at the console of my laptop as a new line symbol, it will come in to the MCU, the other way around. The MCU is putting a character. If I want to put the new line symbol on the stream that is being received by my laptop, then actually it turns out that the software on your laptop does not interpret this properly. So what you want is you want to replace it by this other symbol, /R, which is a carriage return, and that will be interpreted on your console on your laptop as going to a new line. So now we see here a recursive call. I'm going to call this same thing again, but now for this particular character and not this character. And then I'm done. So it's a certain type of programming that I've mixed in here that hopefully you will study and hopefully understand because it's kind of cool to see how you can use those types of techniques to write short, concise code as well. Now what are we going to do here? Well, before I'm going to put a character on my transmission line or in the transmit buffer, I want to make sure the transmit buffer is empty. So I want to wait until it is empty. So let's interpret this instruction. What does that mean? So the last lecture, right, I explained that the exclamation mark here with this expression simply checks whether the expression is equal to 0 or not, right? Is it equal to 0? As long as this is equal to 0, then we are stuck in a while loop. Once it's not equal to 0, we get out. Now what are we looking at? We look at this 8-bit register, we end it with a mask that has exactly a 1 at this particular position. So what I see here will be equal to 0 if the UDRE0th position in this register is equal to 0. Once that changes, we get out of the while loop. So let's have a look back again what that means. So let's go back to that UC SR0A and check this particular position. It says transmit data empty. So as long as it is 0, I'm stuck in a while loop. As soon as it goes high, I'm getting out of the while loop. And what does it mean? It means that one of the two buffers is empty and it's time to refill it. So there is space in my transmission buffer, and that's cool because now I can effectively write my character to the buffer. And remember, this UDR0 is a keyword both used for the transmit buffer as well as for the read buffer, the hardware read buffer and hardware transmit buffer. But in this particular case, I'm writing to it in this construction, so it writes to the transmit buffer, and then I'm done. Alright, so I want to tell you some more about some C coding tricks. Often you will notice that you see these types of instructions because people find this hard to read. It's already much better than just using the constant 5 here, then you have absolutely no clue what's going on here. So UDRE0, for those who have seen the data sheet enough, will be able to interpret this. But this particular building and construction is maybe somewhat confusing. What's going on? It's much easier to have something that says loop, continue looping, loop until the bit corresponding to position UDRE0 is set in register UCSR0A. And you can create some macros, and that's being done in the avrio.h file. Now, in there you see the name for bit positions, registers like DDRX, and I would encourage you to have a look at this file and figure out whether actually the name for the directional register that you use to program the LEDs is actually DDX or DDRX. And that may help you to do some debugging if that is needed. So I'd like you to just have a look at that file as an experiment and find out what you see in there. One of the things that you see in here is something like this. You define a macro that effectively replaces this by this. In other words, you take as input some kind of variable, some kind of constant or whatever it is, and you left shift it. You left shift 1 over that number of positions. You can have here your masking, like the exclamation mark that we have over here. You see it over here. Here you have your loop. You can define loop until bit is set as this whole sequence of characters. Oops. So if you use this particular construct, this macro, as an instruction in your C code, then the precompiler will replace that by this particular string, this particular set of characters. Then it will replace the bit is clear by this particular expression, and then it's ready to go. You can start interpreting that. And it's the exact same instruction that we see here. So there's a ton of macros in this particular io.h that you can use to that purpose. Okay, I just wanted to let you know that there's a lot to learn and to see. Okay, let's go back to the UART. So we have the put character, but we want also to be able to receive characters. All right. So effectively, now we have a while loop here that waits until there is something to receive. Now we're looking at the same register, and now we look at this particular position. So when that bit, the bit at this position in this register is set to high, you will get out of the while loop, and it simply means there's something that was received, so you can read this register, put it into your variable C. And when you have this construction here, when you write this, it means that you're actually reading the receive buffer. Okay, so what we want to do, what we have done is, we have programmed this particular functionality by including a UART put character. Why do we do that? Well, if the UART is receiving if the MCU controller is receiving a character, I'm going to echo it back by putting it back to the laptop, and I will see it printed on my laptop. And that will allow me to verify and check that the MCU actually had received that character. So you can visually see that. And sometimes, maybe a much later block, you will notice that sometimes you get rubbish back. So something strange has happened and you start to wonder why that is. Alright, here's the RC2 table for completeness. So, how do we use UART.c? So we have created a library for you. This stuff is in UART.c. So you're going to now include UART.h. So that means that you can make use of all the functionality that's in UART.c. And that functionality is exactly just the initialization function that I just described, the put character and the get character. Then there's the C construct that creates UART stream as a variable of a type of file, and that means that you need to include a couple of functionalities which you borrow from the UART.h, which is UART.c, which is the UART put character and UART get character. So a file, you want to be able to send and receive strings from that, characters from that. And by doing it like this, this particular UART stream now operates in a way that is being read out by using the get character functionality from this library. And if you want to put things to the stream, you use this particular functionality. Now, why do you want to do that? Well, we want to now set all the STOUT, STIN, STDERR to point at this particular stream. Why do you want to do that? Well, we have all kinds of functionality in our C libraries, like fprintf, fscanf, all the kind of stuff. And all those functions operate with a stream. And that stream uses the STOUT, STIN, STERR. And what I want to do, I want to be able to use those same functionalities without me having to program it again to operate with my UART. If I do not have this instruction, then the fprintf and the fscanf will print to your white area, and your console on your laptop when you run your C program, right? But now you have linked all this functionality to your UART. So now all of a sudden, if I'm going to use fprintf hello, I'm calling the fprintf functionality in my C library that is saying I want to send a few characters, H, E, L, L, and O, and this is linked into this stream. In order to put characters, I use this functionality that I can find in my library, and that's exactly what my library is doing. It's operating, it's putting the character to the transmit buffer on the UART line. So now it's being transmitted like that. So now you don't have to write your own functionality that says I need to write whole strings. So it's a shortcut. You're reusing libraries from elsewhere. So now with this UART.c and this initialization and these lines, you don't have to do anything. You can just use fprintf and fscanf everywhere, and everything seems to be perfectly fine. So what you're going to do is in your tasks, you're effectively going to use this. You want to, first of all, in hardware set up your UART. That is all going to work well. That's going to be the main task, effectively. You're going to do some printing and scanning. And what we will do later on is that we're going to, in the next block, we're going to change UART.c. You're going to change it. Because we have these while loops in there that wait till a character is received or a character is ready to be transmitted. We like to avoid those while loops because that's a waste of resources, a waste of time. We want to make that deblocking. So then we're going to implement this UART.c using interrupt service routines. So that's for a later stage. But for now you're going to experiment with this. And that's it. Yeah. So